Hi, everyone. So we'll just wait maybe 1 more minute, okay, for people to come, and then we can start. Hi, good afternoon. So how's the module three? Yeah, this is a bit longer, right? More, and I guess it's starting to get a bit more technical, especially if you watch the optional section. Yeah, it's very interesting. There are a lot of things to learn, and don't think you can cover everything. Yeah. So, but I think it's a good overview of analytics. Okay. Yep. So a good thing is that next week is a holiday, not like a break, right? Week 4 is there's no new content next week, so it's for you guys to catch up with all the materials that you have learned. Okay. And then there's no office hours next week also. But still, you can email me, right, or Vikesh if you have any issues, and we will also monitoring the Q&A discussion board. So just post your questions there, right? I think the only drawback would be that there is no office hours, so there's nothing for me to present next week. Okay. All right. So some announcements, or one announcement, is that I'm not sure if you've seen the announcement. Just a reminder that the faculty, so Professor UC Keppel and Prasanta, okay, they will be hosting a faculty engagement session on the last of my office hours. Okay, so next week, not next week, the next office hour that I have with you guys will be the last office hours between me and you, and then the session after that will be Prasanta and UC. They will come and they'll be live, and you guys can ask your questions to them as well. Okay, so I reached out to UC and Prasanta, and they're more than willing to come and take over for the one session and see if you have any problems. So I hope you guys make good use of the opportunity to interact with the professors and ask any questions that you want. Okay. All right, so let's start. So today I will be giving you guys a broad overview of machine learning. Okay, some concepts that I think are important for you guys to know. Because there are many machine learning algorithms and practices, right? Okay, but so I can't possibly go through all of them. So it's either I go through one very in depth, right, or I give you some information that is helpful and is applicable to all machine learning algorithms and paradigms. Does that make sense? So that you have a good base and you can understand if you read deeper, then it forms a foundation for you guys to further your understanding. Okay, so I thought maybe that would be more useful because these things that I go through, you most likely with very high probability you will encounter them again as if you read more into the literature of machine learning and data analytics. Okay, so first thing I want to cover is the categories of machine learning. All right. So there are 3 categories, right? The first one, and it's that most people do, all right, is supervised learning. So what's supervised learning? Supervised learning is where you have data that's of this form, right? X and Y, where X are your features or your input, all right, and Y is your output or your response. Okay, so these are data that are basically labeled, right? Okay, and you are interested in finding the relationship between X and Y. All right, and it could be you are doing classification, in which case your labels, right? Okay, your output, the Y variable, is just like categories, right? 0, 1, discrete, right? 1, 2, 3, 4. Okay, but there are really only 6 categories, all right? So it's saying high, low, does the stock market increase or decrease? All right, is this thing good or bad? Right? It could have more than 2 categories, right? It can be high, medium, low as well. Okay, but the idea is that you are categorizing these things, right? There are 6 categories, all right? Or you are doing regression. So regression is numerical. Now notice I didn't say continuous, right? Numerical. So numerical means numbers, right? Okay, it could be discrete numbers. right? For example, the number of goals scored in a soccer match, right? Or the number of products that are bought by a customer. It can be 1, 2, 3, 4, 5, 6, 7, 8 until infinity, but in fact, it's very almost zero probability that it's infinity, okay? But still, there's no upper limit, right? It's not like putting them into categories. Does that make sense? Okay? Or it could be you could predicting like the purchase price, right? Or the demand that is happening. Okay, so these are numerical and this regression, right? So this for supervised learning, we have this feature, all right, about the data. Does that make sense? Okay, so feel free to ask me any questions anytime along the presentation, all right? So this is supervised learning, and then next, if there's supervised learning, then there's unsupervised learning. Okay, so unsupervised learning is data with your only input, and they are unlabeled. There's no why, right? There's no like, this belongs to this category, this belongs to that, okay? Or what is the number of products that this person bought? Does that make sense? Okay. And usually we use supervised learning to represent data in a more compact way. For example, when we want to do feature reduction, okay, we try to reduce the number of features that are in the data set. For example, X could have, you have 10,000 features, all right, or 1,000 features. And then you want to reduce that to only maybe 10 features. So you want to group the similar features together and which features you can throw away. All right. So it's related to like clustering as well, right? You have a given data set, okay, and you're trying to understand if there's any underlying relationship between the data, right? But of course, without anybody telling you there's data. So you are trying to discover is there any pattern in the data just from looking at the data set. Okay. So, or topic modeling. So what is topic modeling? Topic modeling is when you are given a text, right? You want to figure out what is the text talking about, what topic is the text talking about. So every text, there are certain topics that they are talking about, right? Discussing, right? Okay, could be a medical text, it's talking about movie reviews, right? Could it be good or bad, okay? Or if you have food recipes, then you talk about, or food reviews, they talk about why is the food bad, why is the food good, all right? And what is the underlying thing that they are talking about? Is it the chicken? Is it the service, etc. All right. So this is another example of, again, clustering. So this data, they see they are not labeled, and the algorithm is trying to cluster them into the red portions and the yellow portions and the blue portions. So this is unsupervised learning algorithm. All right. So you're basically given all of these points, and they just imagine they're one color, and the algorithm is trying to put them into different segments based on certain similarities that the algorithm finds. Okay. So this is unsupervised learning. And finally, there is reinforcement learning. Okay, so reinforcement learning is where you have data that's of this form. So you have X, Y, and RY. Now X, again, are your input or your features, all right? And Y is your output or your response, so your labels, all right? Or your response, right? If you have X, then what happens? It's going to give you Y, right? Okay. And then what's R? R is a reward of getting this output, okay? And this is a reward function. It could be cost as well, okay? It could be a profit, it could be a cost, just some kind of reward for doing this thing, right? So think of how babies learn, right? They do this thing, they feel pain, then they say, oh, I should not do that anymore. That's how they learn, right? Okay. If you tell them don't touch the stove because it's hot, but sometimes they will just be itchy hand, they will just touch the stove and then they burn themselves, and then now that they learn that, oh, I should not touch the stove. Okay. So the idea is the same, right? You give the algorithm will have certain actions that they can do. Okay. They do the actions. Okay, based on the features, they observe the feature, they do an action, and then they receive an output, all right? And then that output will correspond to some reward, okay? And then after that, they will decide, should I do this, is this action good or not, all right? So there's some delayed partial feedback from the action. So this reinforcement learning, a lot is really used nowadays, okay? A lot of the things that you see in the media, they are an application of reinforcement learning. For example, learning how to play a game. Okay, like the most famous example I went through in the previous office hour, one of them is AlphaGo, right? Playing Weiqi, right? The black and white chess. Playing chess as well is also reinforcement learning. Okay, driverless cars, right? Okay, we are going towards driverless cars. This is also done using using reinforcement learning. Okay, so I have a video here on reinforcement learning. You can see that.
On Earth, the simple rules of natural selection and competition led to the evolution of increasingly intelligent life forms. Today, we ask if comparably simple rules and multi-agent competition can also lead to intelligent behavior in a new virtual world.
So you can watch.
These agents are playing hide and seek. These agents have just begun learning, but they've already learned to chase and run away. This is a hard world for a hider who has only learned to flee. However, after training in millions of rounds of hide and seek, the hiders find a solution. The hiders learn to use rudimentary tools to their advantage. By grabbing and locking these blocks, they can create their own shelter. The seekers are locked in place for a brief period at the start of the game, giving hiders a chance to prepare. Even so, the hiders must learn to collaborate, accomplishing tasks that would be impossible for any single individual. The hiders are not the only ones who can learn to use tools. After many generations of failing to break into the shelter, the seekers learn to jump over obstacles using ramps. However, after many millions of rounds of having their shelter breached, the hiders learn to take away the primary tool the seekers have at their disposal. Note that we did not explicitly incentivize any of these behaviors. As each team learns a new skill, it implicitly changes the challenges the other team faces, creating a new pressure to adapt. We've also put these agents into a more open-ended environment, randomizing the objects, team sizes, and walls. In this world, they learn to construct their own shelter from scratch, requiring that they arrange multiple objects into precise structures. To prevent seekers from using the ramps, the hiders move them to the edge of the play area and lock them in place. We originally believed this would be the final strategy that the agents learn. However, we found that after more training, the seekers discovered that they can jump on top of boxes and surf them to the hider's shelter. In the last stage of emergent strategy that we observe, the hiders learn to lock as many boxes as they can before constructing their fort in order to defend against box surfing. So how do agents acquire these skills? They're trained using reinforcement learning, an algorithm inspired by the way animals on Earth learn. The agents play thousands of rounds of hide and seek in parallel for many days. They train against each other as well as past versions of themselves using an algorithm called self-play. Co-evolution and competition on Earth led to the only generally intelligent species known to date, humans.
Okay. So can you guys hear the sound actually? Because I can't hear the sound by the video, but in the video on my side. But I think you guys should be able to hear the sound, right? Okay. So basically, you see that we don't program them to do all these actions, right? The computer, I guess the video will explain what they are doing, right? Okay. The computer does not know all these actions. They just over millions of rounds, right? They try to do all these actions. And they explore, okay, and then they figure out what are the best actions to do. All right. So Nicholas has a question. It says, for AI use cases in video analytics, is it more supervised learning or reinforcement learning, or are both used, right? Okay. So for video analytics, it's usually actually it is supervised learning, right? So someone has to label the videos first, right? Okay, and then after that, there's reinforcement learning as well, and it also, if you really want, there's also unsupervised learning, right? It just depends on your use case as well, right? So most of the time there is usually supervised learning, all right? And there's a deep neural network going on there, and usually we need some kind of supervised data, all right? But there's also reinforcement learning for video analytics, okay? And it's deep reinforcement learning, all right? So basically the answer to your question is that everything is used, right? And also it depends on your use case, all right? Not only unsupervised reinforcement, there's also supervised learning, okay? All right, so let's go, let's continue. So here I just summarize it into this diagram for you guys, right? So learning, there are three types: supervised, unsupervised, and reinforcement. And then in supervised, there's classification and regression, all right? So this is a paradigm, like some kind of framework that you can follow and understand, okay? Now this is for supervised learning, but the idea is the same for other paradigms of learning, all right? It's just that this we can generalize this, okay? But it's good to just understand this. So what we are trying to do in learning, in supervised learning, okay? So for example, all right, we have some unknown target function that we are trying to learn, okay? We do not know this, we do not know this target function, right? So for example, X is the customer features, right? This is a bank, right? We are talking about credit approval formula. So X could be your income, your age, right? Your job, okay? And Y is whether you will pay back the loan or not, right? So there is some formula, right, that relates my age, my income, my job to the probability, or to me being able to pay back that loan, okay? But we do not know this formula. And what we are trying to do is to learn this formula F, okay? And or try to find a formula that is as close to this F as possible, okay? How do we do that? We can observe data, right? Historical records of credit customers, right? Okay, so we have here X1, Y1, X2, Y2. These are individual customer data points, all right? And then suppose we have capital N of them, right? Okay, then what do we do with this data? We feed it into some kind of algorithm, right? So these are here all your different types of machine learning algorithms, right? Okay, and how do they learn? All right, there is a hypothesis set. Okay, we call this H. It's a set of candidate formulas. Okay, so all the different, depending on what type of formulas you put here, then the algorithm can learn, right? Okay, so whether you want to use X, you want to use X squared, or whatever different other algorithms or functional mathematical functions they want to use to relate X to Y. Does that make sense? Okay, and then the algorithm will pick the best one from here, and it will come out the final hypothesis, right? Which is your learned credit approval formula, right? Which is called G. And we hope that the algorithm can give us a G that is as close as possible to F. Does this make sense? Okay, so this is the fundamental idea for all supervised machine learning algorithms. All right, there's a set of hypotheses. You think, okay, maybe this works well. We check. All right. Okay, if it gives me a good prediction rate, okay, then maybe that's it. Then we compare with another one from the hypothesis set, and then we iterate through everything, and then finally we get one that is the best, and we hope that this best is a good approximation for F. Okay, so this is the idea, right? For reinforcement learning, for unsupervised learning, you can modify this setup a little bit, but the idea is the same. There's some algorithm that trains on your data set, and then they give you a final hypothesis of the relationship between your X and the Y, or just the X. Okay, does that make sense? Right, so this is the setup. Now, I want to talk about bias variance trade-off, okay? So this is a very important concept in machine learning, all right? So now let's talk about what is bias, okay? So bias is how much the average function that we learn using different data sets deviates from the target function. So, okay, so let's try to understand bias first, okay? So now, let's go back to this setup we have, right? Now, the historical data, right, depending on history, right, is random, correct? It's not all the time you get the same historical data, right? So you can have different training historical data, right? And different training historical data, all right, after you apply the learning algorithm, will give you a different G, right? That is again close to F, okay? But because this G is trained on different data sets, you will get a different G, right? Most of the time, right? Likely you will get a different G, okay? Now we can talk about an average G, right? Over all possible data sets that we can, samples that we can draw, there's an average G that we will get, okay? And how far this average G, all right, deviates from the true F, that is the bias. So think about this one, okay? Let's look at this picture over here, right? Now this is one dot. So now in my H, if you remember, H is my hypothesis set, okay? So H is here, my hypothesis set, the set of candidate formulas. If I only have one dot in my H, which means that I only have one candidate formula in my H, right? Then no matter what data set that I use, correct? I will just tell you that, oh, this is the best function because I only have one candidate, right? So I'll give you this candidate. Does that make sense? Okay. Then the distance, so the average of one thing is just going to be itself again, right? Right? If you always give me the same thing, no matter how I change, the average is still going to be the same thing. Okay. And the distance of this thing from my F, my true F, is known as the bias. Does this make sense? Okay, please ask any question and stop me if that doesn't make sense. Okay, so this bias, this is the distance between your average prediction and the true value. Okay, because your prediction is going to change depending on the data set that you draw, right? That you have, right? Okay, but you can draw many data sets, okay, and get an average prediction, right? And the distance, the error, right, of the average prediction from the true prediction is known as the bias. Okay. Now, next, let's talk about variance, right? Now, variance is how our predictions from different data sets will vary about the average prediction. So now let's look at this diagram here. Okay, it's trying to illustrate variance. Now, again, we have a hypothesis set, right? This H, right? And you see that there are many dots in this H. So we have many candidate functions, all right? Now, the true F is inside my H, right? So if I give you one data set, maybe this time it will give you this dot over here, right? If I give you another data set, then maybe now it'll tell you, oh, this is the correct one, right? Now, if I change the data set again, now maybe they tell you that this one is the correct G. This is the best G that we can find, right? So this is all the different G's that we can find. All right, if we do many different data sets, we take the average of the G's. Most likely, the average of all these data points is going to be the middle over here, the F. Does that make sense? All right, so that is again still the average function, right? Now the variance is what? The variance is how all these things can change, how my G can change. Do you see? So my G, if you give me different data sets, okay, my G will change inside this shaded circle, right? That's the variance of my prediction, right? The variance of the function. Does that make sense? Okay. Do you see the difference between bias and variance now? Okay, bias is the average dot of all these dots, okay? Variance is all the different dots that are near the F that I can get if I change the data set over and over again. I change the data set, if I have high variance, right? My current prediction will jump from here to here, right? If I change another data set, now I'm going to give you, oh, the best prediction should be here, right? I change the data set again, I'm going to give you this other prediction. So this is the variance, you see, the variance of the prediction. Here, we have no variance, right? In this, on the left-hand side, you only have one prediction, 0 variance. No matter how I change the data set, I give you the same prediction because I only have one target, one candidate function anyway. There's 0 variance in the candidate function. Here, all right, you change the data set, I cannot obviously predict here, it's very lousy, right? Our algorithm is very lousy, okay? Even a good algorithm will predict somewhere here, right? But they cannot, you know, depending on the data set, they'll tell you different predictions. And then that's the variance of the prediction. Okay, now there's this thing known as the bias variance trade-off. Now, oh wait, before we go there, okay, now another example to tell you what is bias and variance, right? So this is the target function, right? If you have low bias and low variance, means we hit the target very well, and we are very close, and our like grouping is very small, right? Okay, we are all grouped very closely, very tightly together, okay? Now, if we have low bias but high variance, means we, you know, on average, we hit the target, but we are very sparse, right? We have high variation in our prediction, in our target, okay? Hitting the target. Now, this one is a small variance, but we are very far away from the target, right? We are, you know, it's accuracy versus precision, right? So we're not very accurate, we're quite precise, okay? So this is low variance but high bias, right? We are far off from our target, but still we have low variance. And then this is the worst. We have low variance, we have high variance and high bias, okay? So I hope this is also another good idea to illustrate bias versus variance, okay? So now let's try to consider what is the bias versus variance trade-off, okay? Now, consider we have a target, this is a true function, it's a sine function. So sine function looks like this, okay? So just imagine, we are trying to learn this curve. The true function is this curve, okay? And then H naught, okay, which is my first hypothesis set. My first hypothesis set only contains straight lines, okay? So you look here, okay? My hypothesis is only straight lines. I can only use straight lines to estimate the curve, okay? The second hypothesis at H1 is that I can use all lines, not only straight lines, okay? I can use any line, okay? As long as I can use slanted lines, horizontal lines, vertical lines, okay? I can use any of these lines to try to estimate the curve, okay? So if you use H0, we only use straight lines, right? My average prediction is just going to be a straight line also, right? Which is this folded straight line over here. Okay, so this is my G bar, my average prediction. And you can see the distance between G bar and the true F, that's going to be by bias. Okay, and this bias is going to be high because after all, we're just using a flat line to estimate the curve, right? So we're going to have a lot of error. Okay, does that make sense? But the variance is going to be smaller because they're all flat lines, okay? And they are flat lines just over here. But you compare over to this one in this hypothesis set, if I'm going to use all the slanted lines, I am going to have a lot of variation in my prediction, right? Sometimes I'm going to, depending on the sample that I draw, sometimes I will get this prediction, sometimes I'll get this prediction, right? Different slanted lines. Over here, depending on the sample that I draw, all the time I'm just going to get this horizontal line, right? So it's not, you know, the variation is not too bad. Here, sometimes I can go from an upward sloping curve, a line, to a downward sloping line, right? The change is going to be a lot. The variation is going to be a lot, okay? But on average, my prediction is going to be much better because I can, on average, I'm going to use a slanted line to predict this one. You see, this seems to be a better fit than this line, right? Okay, so the bias here will be smaller, but the variance here will be very large because I have a lot of different predictions depending on the sample that I can get, okay? So there is a bias variance trade-off over here, right? We can have low bias, we have a high bias but low variance here, or we can have low bias, but high variance. Okay, and you see that the variance and the bias comes also from the candidate set, right? Now, how flexible my candidate set can be, right? Here, I'm just limiting my candidate set to horizontal lines. I'm not very flexible, right? I can only predict horizontal lines. How flexible can I be? Okay, now here, I'm extending the set of candidates, right? I can have horizontal lines as well as slanted lines, right? So I have more flexibility. But because of the flexibility, okay, I introduce more bias. I introduce more variance, but I reduce the bias because I can predict much better on average. Okay, but my variance is going to increase a lot. Okay, now you can think about it. If we introduce a x square over here, right, to maybe another hypothesis, then we have even more flexible. All right, so I can on average I'm going to predict much better, but my variance is going to be very high, or my variance in my prediction is going to be very high. Okay. So there is a bias variance trade-off. Now, this is the bias variance trade-off that I'm talking about. So the more complex is your model, okay, the lower is your bias. The better on average you're going to get the true prediction, okay? On average, it means that if you give me different data sets, I take the average of my predictions, I'm going to get the true target, right? Okay, but because the model is really complex, all right, if I change the data sets, right, my predictions are going to change a lot also because of the complexity of the algorithm, okay, the model, right? So different data sets are going to give me different predictions, and this is going to result in variance, right? And this different prediction is going to result in error as well in my prediction, correct? Okay, and we cannot say average, right? Okay, so now there is an optimal model complexity, all right? And this is called the bias variance trade-off. We don't want our model to be too complex, all right? So that then if it's too complex, we have very high variance, there's a lot of errors still, all right? But if we are too too simple, right? Our model is too simple, then we have really low variance, but then we don't predict very well. Then we have very high bias, okay? So there is a sweet spot. And this is called the bias variance trade-off, right? We make the model more complicated, we increase the variance, but the trade-off is that now we can lower the bias, all right? And the best part will be somewhere here, right? The best model will be like maybe here, right? Okay, the optimal model, but here they say it's here, okay? So it's just here, right? This is the two add together is this one, right? But you get the idea, right? Okay, this bias variance trade-off. So it's not all the time the most complex model is the best, right? Actually, so now we learn, it's not the most complex model that's the best. Right? It's a somewhat medium complex model. Okay? So this is a very fundamental concept in machine learning, and you will always encounter this, right? And you see that no matter what model that you use, you will always have this bias variance trade-off. This is model complexity, nothing to do with linear regression, random forest, but every model will have this problem. All right? Okay? So I'll give you another example. Say we want to, this is the samples that we get, right? This cross. If I just use a very not so complex model, simple model, straight line, I fit like that, okay? High bias, you know, I don't fit very well. If I look over here, I can use a super complicated model. You see x, x squared, x cubed, x4, right? I can fit a curve that passes through all the points. Wow, very good, right? But of course, if you just think about this, this is going to be overfitting, right? This is going to introduce a lot of variance, right? Low bias, but a lot of variance. And the best one is somewhere in the middle. You don't want it to be too complicated. You don't want it to be too simple, somewhere in the middle. And we look at this, our intuition will tell us that this will be much better prediction than this, right? Does that make sense? Right? You look at, this is a very flexible model, very curved. You can let it curve anywhere you want, okay? But obviously, if we look at this, intuition tells us that this is going to be the best, correct? Does that make sense? It's very unlikely that my data follows like, my true data follows like that, right? Okay? So this is again illustrating the difference between bias and variance. Okay, this is low bias because, okay, on average, we're going to predict very well, all right? But for each individual sample, we're going to have all these variants, right? And this is the best. Okay, another one here, another example of the bias variance trade-off. Now you look at the picture on the left, all right? This is like in clustering, okay? So not only in supervised learning, in clustering as well. We're trying to cluster these things together, okay? Now, we're trying to group the orange and the blue. So if we use so if you look at the second figure, the middle figure, if we use a very complex model, right, that can capture all these oranges, you see, basically you just kept putting all the orange together and all the blue together, right? And then this part has no blue, so you just call it orange. Okay, so even your 1-year-old or 2-year-old child can do this, right? Just or tell a child to, how do you want to color it, or just put all the red to all the orange together and then all the blue together, and then we can cluster that, right? Okay. Now this high complexity model is going to be very bad to predict new data because you see, right here you produce orange and it's supposed to be blue. I think a better one would just be one cut over here, right? Somewhere like a nice, very nice cut over here, and then on the bottom corner, right, there is a. So you just label it as orange, and the top corner just label it as blue. Okay, but again, here we are illustrating the bias variance trait. Right, so don't always use the most complex model. Okay, so just to illustrate again, right? There are many codes, right? The idea is that, okay, the simplest model that fits the data is also the most plausible, right? Okay, Occam's razor, if you heard of Occam's razor, right? The more assumptions you have, the more unlikely an explanation is, right? We prefer the simplest explanation. All right, okay. And then the less complex a machine learning model is, right? The more likely that your good prediction, right, is not because of that particular sample or your machine learning. It's more likely that it's because your model is performing really well, right? Because you're a very simple model, right, and you can do very well. So it's not because that you have a very complex model and you do very well, okay? It's because you have a simpler model. Then it's easier to convince people they are not overfitting. Okay, so this is the bias variance trade-off that I want to go through with you guys. All right, and then now let's talk about training, right? Because we talk about learning, machine learning, right? You must train the algorithm, understand a little bit about how we train algorithms, right? So at least in supervised learning, all right, machine learning algorithm use the model by examining your data, right? Okay. And then you find a model. So this is our H, right? Remember, we have a target F, and then we have a model H, right? Many H's, right? You find the best H, okay? So how do you do that? We minimize some kind of loss. Now, what is the loss? So in linear regression, it will be the distance between, right, the data point and my target function H. That's not target function, my candidate function H. So this blue one, if you remember the setup that we had earlier, the blue one is my hypothesis, okay? My candidate model, right? The blue one is my candidate model. Now, on the left one, these circles, right, they are the data. If this is my candidate model, this is very poor prediction, right? I have very high loss. Okay, the distance between my sample and my predictions are going to be very far away. Now, this model on the right, okay, the distance between them is going to be smaller. So this model is going to be better, right? The loss here is smaller. Okay, and what we do is we add up all the loss. Okay. Now, the problem is when we're adding up the loss over here is that we have to take some kind of measure of distance, right? We cannot always take top minus bottom, top minus bottom, top minus bottom, top minus bottom. If we do that, top minus bottom and this top minus bottom, this is going to give me positive distance. This is going to give me negative distance. I add up the distance together, it's going to give me 0 sometimes, even though it's not, right? Does that make sense? So how do we deal with negative distance? We square that, okay? So there is this thing known as the mean square error. Now, this is one of the most common measures of loss, measure of distance that you'll use in machine learning. You always see this mean square error or the root mean square error. Now, the root mean square error is just the root of this thing over here. Okay, the square root of this thing over here, the whole thing. All right. So let me explain this formula. It's very easy. It looks very complicated, but it's actually very easy to understand. You look at the picture on the left. How do we calculate this mean square error? It says y. What is y? Y is my actual data value on the y-axis here, right? So here, my actual y lies on the line. So y minus my prediction. My line is my prediction, right? So y minus my prediction is 0, correct? Now here, my y is 1 unit above my prediction, right? So y minus my prediction is 1, correct? So you can do this for every point over here. Here, my y minus prediction is 0. Here is minus 1. Here is 0. Here is minus 1, 0. Here is 1, 0, 0. Correct? Okay. Then we square all of them. So minus 1 when we square, we'll get 1. Minus 1 we square, we get 1. Then we add everything together. Do you understand? So basically, mean square just say, oh, I measure the vertical distance between my point and my prediction, right? My line. I square all of them and then add together. That's it. That is mean square error. Oh no, I haven't finished this one here. We need to take the average because mean means average, right? Mean means average. Mean means average. Okay, the mean means average, expectation, average. So we need to take the average over all my points, and that's the average error for each point. Does that make sense? Okay, so this is a measure of loss. for a function. There are many different types of loss function that you can use, right? Again, just now I said there's a root mean square error, but it's basically the same. There is also the AUC curve. There are many things, right? But basically, we want to choose a model that gives us the lowest mean square error. For example, if we are using mean square error as a measure of the fitness of my prediction, right? How well my model is. Okay. Now, why are there two pictures I show over here? Because now let's see. I want to compare which one do you think has a higher mean square error? Is it this one or this one? Why is it not so intuitive? Why? Now look over here. Here I have 4 points that are not on the line on my prediction, right? Okay, for the same number of points, right? 10 points, okay? Here I have 4 points that does not lie on the line. Here I only have 2 points that do not lie on the line on my prediction. So here you think that I predicted 8 out of 10 correctly, like exactly. Here I predicted 4 out of, no, is it 6 out of 10 correctly, right? But which one has the lower mean square error? Now we calculate, now let's try to calculate mean square error again, right? Another example. How do we do that? We take the distance from my dot to the line and square it and then add together and then average out, right? So here everything is 0, on the line is 0. Here will be what? 2 units, and here will be minus 2 units, right? We square that, we get 4 units here, and we square minus 2, we get 4. So here is 4 and 4. We add them together, we get 8, and we divide by 10. Because we have total, our capital N is the sample size. We have 10, the sample size here is 10. So 4, so 2 squared plus minus 2 squared, we add together is 8, divided by 10 is 0.8. So my mean square error for here is 0.8, right? Okay. Here, my mean square error is what? So again, on the line, it's all going to be 0. Here it's going to be 1, minus 1, minus 1, 1, right? We square that, it's just going to be 1, 1, 1, 1, 1. We add together is 4. 4 divided by 10 is 0.4. So this model has a lower mean square error compared to this model. This model is 0.4. This model is 0.8. Okay, so you see that even though we predict everything on the line except this 2, 1, this one has a lower mean square error. Okay, so because we squared, because the further the distance is away, the more weight there is on it, right? Compared to nearer. So this is better, right? Okay, but don't worry, a computer always calculate all these things for you, right? Okay, but why we calculate now for a small sample size is so that we can understand the formula better and understand what is mean square error better. Correct? Okay. So machine learning models, they aim to make good predictions on new, previously unseen data, right? Because if it's unseen data, what's the point? We already see the data. So we want to be able to make good predictions on unseen data, right? But given a data set, how would you get, new data, unseen data? It's expensive, right? If you throw the data scientist this data set, and then the data scientist can ask you, can you give me, I want to get new data, right? Then that's not very good, right? You spend money, you need to spend money and time to get new data. So I have a question. So which model is better, W, lower MS? So this model on the left is better. So we want to have a lower error, right? Because this is a measure of the distance, right? Okay, so this one is the measure of the distance. This one is not the measure of the, okay, no. So MSE is a measure of the distance of my average distance of my points to the line, okay? So for this model is better because it has a lower mean square error. The lower the mean square error, the better. Right? If the mean square error is 0, think about it. My mean square error is 0, means on average, my points all lie on my prediction. I predict very well. Okay, but then if you get mean square error 0, you must think very carefully something is wrong. Not possible to get mean square error 0, right? You must have overfitted. You predict everything the same. Okay, I hope that answers your question. Nicholas, in the second model, we have more actual points on the prediction line. So there's high variance but lower bias. Now this one is hard to say, okay? Because actually for these two models, it seems that they have the exact same variance and bias because it's the exact same models. Do you see that? Okay? But we do not know because it depends on the model that we see, okay? The variance and bias does not depend on the data points itself. It depends on the machine learning algorithm and your hypothesis set, your set of candidate functions. Okay, so you have to consider the entire set of the candidate function, the complexity of your model. Okay, it does not depend on the data point. It depends on your machine learning algorithm. All right, the higher variance and lower bias stuff depends on the complexity of the model that you're using. So it depends whether you are, for example, whether using only straight lines, using only curved lines, right? or you allow very, very funny lines, okay? Then if you allow many, many funny lines, we have very high variance, okay? But lower bias in our model, okay? If we only allow flat lines, horizontal lines, then we have very high bias, but low variance, okay? It's nothing to do with the data points itself. It has to do with your machine learning model, right? The model, is it complex or not? So a complex model is a model that allows many, many very funny shapes of your lines. Think about that, okay? A less complex model only allows maybe straight lines. Does that make sense? Okay, I hope that answers the question. If not, please ask me again. Okay, so, so again, just think of straight lines and very funny curvy lines, right? Curvy lines will give you lower bias but higher variance. Straight lines will give you high bias but low variance. Okay, so you can go back and look at the slides again, or we can check after the thing. Okay, so now how do we get new data, right? So what we can do is to split our data into two subsets. Okay, the first subset is called the training set, and the second subset is called the test set. So this is what we usually always do, right? We have a training set and a test set. Okay, and then we train our machine learning model on the training set, and then we test on the test set. Okay, or in other words, we validate it on the test set. So this is called validation. How do we know whether our model is good or not? We test it on the test set because we train on the training set, right? Means the algorithm has never seen the test set, right? It's never seen the test data. Then we use the test, we predict on the test data and see whether our predictions are good or not. And that is the test set, okay? And how do we know it's good or not? We use the mean square error, right? If the mean square error on the test set is low, then we know that our prediction, our model is really good, okay? So this is, of course, well, if you use the test set must be large enough, okay? And you don't cheat by using the same test set over and over again, right? Okay, then I think then that's not so good, okay? Does this make sense? So this is the idea. I think this idea everybody knows, right? Training set, test set, okay? Now, usually we do like 82, no, we don't really use this, but I'll talk about why we don't really use this later. Okay, let's continue. So the framework is like that, right? We have a model, we train the model on the training set, right? We evaluate the model on the test set, right? We get a mean square error, the lower mean square error, the better. Then we tweak the model, right? We try to see, okay, maybe now I want to improve the model, I include this feature or I don't include that feature, right? So I include a feature, I train again, I evaluate again on the test set. Then after that, I see, oh, maybe now my mean square error is lower, so this model is better, right? Then after that, I go. Okay, then we just repeat this whole thing, then we pick the model that's the best. Does that make sense? So this is the standard workflow. Now, Ango, I guess, sorry, I pronounced your name wrongly. I'm very bad with names. So the weighted for each set should be 80% for training and 20%. Okay, so this is 80% and 20 is the kind of like the rule, but there's no rule, right? It just depends. People just come up with 80-20. It could be 50-50 as well. Why it cannot be 50-50? It can be 60-40, right? It can be 70-30. There's no rule, okay? But of course, nobody does 10% test set, a training set, and 90% test set. That's lucky, okay? But there's no sweet, so there's not really a sweet spot. 80-20 is just what people normally use. Just like how, when you talk about statistical significance, people just decided, oh, 5% is statistically significant, then that's it, everybody is using 5%. Okay? But like, so I hope that answers your questions. But we will see later, we don't really exactly follow this particular workflow. Okay? So let's go to the next one. So for this workflow I'm going to show you, we also don't really exactly follow this one, but I will show you, later I will tell you, okay, so I'm taking your like, suspense, right? Keeping suspense, okay? You'll build up to the idea, okay? So now the training set, now what is happening here? Because over here, what's the bad thing about here? You're always performing on this test set, and then you pick a model that does best on the test set. So there's a lot of reliance on this test set, right? And there's only one test set. So we can improve this a little bit by splitting my data into training set, validation set, and a test set. So we can do the same process on the validation set, right? We pick the model that does the best on the validation set, and then we confirm the result again on the test set. Because there's a lot of reliance here on this test set, and then we pick the model and test set. right? So we want to see that, or maybe it's because it just works well for this particular test set. So does that make sense? So we do it, we just to be doubly sure, we do it, we don't want to make sure that it's only because of this validation set. Sometimes, you know, you're unlucky just because of this validation set. We confirm again on a test set that we leave out from the very beginning. Does that make sense? Okay. Now, what are the disadvantages of this framework? Now, data, if you have watched the video, data is a very critical resource, very precious for data scientists, right? If you ask a data scientist, do you need more data? No data scientist will tell you no. They'll just say yes, right? You ask them how much data you need, they'll tell you as much as you can give me. Okay? No data scientist will tell you, no, I have enough data. I can do everything in the world. No, okay? If a data scientist tell you that, you just tell me, thank you very much. I'm going to find another data scientist. Okay? We always say we want more data. Okay? So what is wrong with this one? We are given this data, and now we cannot use, you know, depending on how we split, we cannot use this portion of the data. But data is so precious to us as data scientists, correct? So one thing that we do, how do we overcome this? So first thing, after we pick the best model, we will retrain the whole model on the full data. Okay, we use the full data as the training set. That's one thing. Okay, but that's still again not so good because in my training that time, I'm only using this part to train, right? I'm testing on this, right? So there is a way to overcome this, and it's called validation. Okay, so now let's look over here. This is another problem also. Okay, so not only the data problem, the second problem they have is depending on how you split, right? The validation set, right? You're gonna get different results. So on the left here, okay, I'm just training a model, okay, with certain mean square error. Remember, the lower the mean square error, the better. Okay, so you see, we have degree of polynomial is the complexity of my model. Okay, so what kind of polynomial do I use? Do I use a straight line, which is degree 1? Do I use a curve, which is degree 2? Or even more flexible curve, you know, higher degree polynomials? Okay, now this is for one framework that we use here, right? We split the data set into training set, validation set, test set. We test it, we get the mean square error, and that's it. But the problem is, why must I split this particular portion, correct? It should be random, correct? I can randomly split my data into validation set and test set, right? For example, this I can if by luck I just decide I want this portion to be my validation set and this portion to my test set, I'm going to get a different training set and test set. Does that make sense? Correct? Okay, for the same training set, I can split different parts of the data to be my test set and validation set, right? It doesn't always have to be the end, right? It can be the front, right? Right? Then the back of my data is the training data set. So what is happening? So let's look at the right graph here. This right graph is the same algorithm, okay? And the same data set, but different parts of it is split into the training and the test data set. Okay, so it does it 10 times, right? You just have 10 different splits. Okay, not about, even if we keep the proportion the same, we keep the 80-20%, whatever proportion the same, the size of the, if we keep the size of the validation set the same, we can still choose different parts to be the validation set, right? So this is what is happening over here, right? We pick different parts of the data to be the training set. You see that just by changing that, right, my performance is going to be very different. Does that make sense? See the orange one? This orange performance is so much worse than this yellow one. And the only difference is because it's not I generate new data, I use the same training data. I use the same data set. It's just that I split it at different points. Okay? So this is the weakness of this particular method, right? Okay? The only thing that we can see from here is that what? We shouldn't use a first degree polynomial to estimate, right? Because you see every time you jump from 1 to 2, it's going to be very lousy. But then we cannot tell how good is our method. Okay, which one is the best, right? Because it's depending. Here, sometimes this pink one become better than the blue one, right? So should we use, the pink one become worse than the blue one. So should we use the blue one here or should we use the pink one here? Okay. Now, how do we overcome this problem? So then therefore we have this thing. Now this is what people are using in, if we cannot fit the model to the, okay, wait, so let me answer Nicholas' question first. If we cannot fit a reasonable model to the training data set, we suspect there's a problem with the data set. They always blame the tools, right? No, okay. Usually we do the best that we can, okay? Then we try to ask for more data, okay? Or it could be because your model is not well, okay? You need to use a different model, okay? Now there's no one model that fits everything, all right? You will find that different models will work well with different data sets. So you have to try many different models, all right? Could be that random forests work well for this one, but random forests work very lousily for another one. It could be linear regression works well for this one, but linear regression works very lousily for another one, okay? So you have to try, that's why we always are trying many different models, right? There's no one model fit all, okay? You can always construct a data set that works very lousily for your model. And same thing, you can always construct a data set that works very well for your model, all right? So you must always, so whenever we are choosing models, right, there's not always one model. We always must compare between many models. Then you will know whether it's good or not, right? You have one model, you cannot know whether it's good or not. Even if the mean square error is very low, you have that one model only one. Maybe another model will give you an even lower mean square error, then that model is actually lousy, all right? How you know something is good, now this also is with real life, right? How you know something is good or not, you must always have a baseline to compare with, right? Right? If you someone who has never eaten chicken rice before eat chicken rice, you say, wow, this chicken rice is very nice. You believe him, man, because this is the first time he eats chicken rice, right? He must eat many other types of chicken rice just to know whether it's good chicken rice or not, right? Correct? Okay. So now let's go back to this leave one out cross-validation. So now what is leave one out cross-validation? This is taking this idea of the validation set and test set, okay? Splitting your data into the training set and the test set to the extreme. We leave one data point out, okay? And then after that, we use the rest of the data points as my training set. And we use that one data point as my test set. Does that make sense? Okay, so that's why you say leave one out. So this is my data set. I have n data, right? N data points. I leave one data point out and I train on all of the rest of the samples, right? Then how do I calculate how do I do my test, my validation, my validation? I just validate on that one data point. Okay, I just validate on that one data point. Then I have this mean square error. So if we can leave this one out, then we can also leave the second one out instead of the first one, right? So we can do the same thing, but now we leave the second data point out. Okay, and then we calculate the mean square error for that one by checking the mean square error after we train on the blue portion, the rest of the data. All right, we train and then we test on just that one data point, okay? And we can do the same because we have n data points, right? So just do for n, right? So we will get n different models, okay, with this mean square error, right? Okay, and then we can take the average of this mean square error. So this is called the cross-validation error, okay? The cross-validation error, CV, cross-validation, okay? We'll give a score, and this is the score that we'll use. Does that make sense? So this overcomes this problem of, I cannot use all my data set, right? Okay, I use one particular data set and then I take the average. Then we hope that this again gives me will be able to overcome the problem of of the different of the performance, right? Depending on the split. You see here, the performance depends on the split of the data, right? Now what I'm saying is that I split I split individual data points and then I take average over all the data points. Okay, then that's my cross-validation score, and that is how I overcome that problem. Okay, but there is one issue with this problem also. So we use 2 parts, not 3 for each n. What does that question? Yeah, we use 2 parts only, correct? Okay, so we only have a test set and a training set. Okay, we don't have the validation set. No, sorry, we don't have the extra. If you think about it, we don't have the extra validation set. Okay, does that make sense? Now, this validation set is not as important as this cross-validation method that we are doing. Okay, because the validation set actually is just an extra layer of assurance only. You can still do it. You can still do you can still leave out the cross. You can still combine this one with the cross-validation, but then you must think carefully. Okay, now you must split the data into 3 parts. Then you have one again. Then one part is validation, one part is test, and another part. Then the combination is going to take a very long time to do that, right? So we probably don't do that. We just maybe the easiest way to do that will be split validation out and everything. Okay, but like I said again, usually it's just leave one out cross validation, and this is good enough. All right. Now the problem with this is that if you have 1 million data points, you're gonna take 1 million. In each model takes 0.1 second to calculate, 1 million data points per 1 second is 100,000 seconds, okay? Who has the time to wait for 1,000? Maybe you have, okay? But a lot of times we want it to be fast as well, right? Okay, so this is computationally expensive, right? Now, if big data, you have tens of millions of data points, you can't expect to do this, iterate this tens of millions of data points, right? And then, okay, every time you want to run your model, you run one model only, you take 1 hour. You want to run 10 models, it's going to take 10 hours, okay? So how do we improve this method? Okay, we do this thing called K-fold cross-validation. Now, this one is the one that you probably would have seen many times, okay? The K-fold cross-validation. What is K-fold cross-validation? K-fold cross-validation is actually the more general version of this. Instead of splitting into one data point and everything, let's say this one, here we are illustrating 5-fold CV. So we split the data into 5 portions only. First portion, second portion, third portion, fourth portion, fifth portion. All right, we calculate for these 5 and we take the average. That's it. So instead of one, we split the data, instead of one data point, we split into groups, right? Okay, one small group and then a larger group. We do this for 5 times, okay? So we basically separate the data into 5, and then we take the first portion as training, first portion as test, the next 4/5 as training, and then now we take the first and this one to be training and then this one to be test, and then we do the same. We get 5 different mean square error, we average it out, and then that's it. Okay, so the K-fold validation. Now this leave one out cross validation. If you think about it, it is the special case of the K-fold cross validation. Just that my K-folds, how many folds I have? I have n folds because I have n folds, right? N folds, right? I just n folds means each group only one, correct? Here I have 5 folds, so each group is n divided by 5, something like that. Okay, does that make sense? So this is the one that we always use. Okay, K-fold cross validation, and this will overcome the issue. Now, then you're gonna ask me, okay, wait, let me answer this question again. So wouldn't machine learning be able to deal with zillions of data sets? If not, if so, no need to do K-fold. So again, it will take very, very long time to do zillions of data. Okay, now some models take very long to run already, even on one thing. Okay, some models take very long to choose the functions, right? Then after that, after you choose a function, you are going to do that whole thing again on another sample and another sample that you remove one particular value. Okay, so that's going to take very long again. Okay, so and also the K-fold is also not so much on the sample size, but more on cross validation. Okay, we want to make sure that our mean square error is actually correct. Okay, so we are using all the data points. Each data point, you see, this data point first is used in the test set, but then in the next 4 models, these data points are used in the training, right? Compared to earlier, okay, these data points are never used in the training. Does that make sense? They are always in the validation test set. That's all. Only these are used in the training. For cross validation, one advantage also is that we will use the data set, the entire data set. Okay, but sometimes it's going to be the test, sometimes it's going to be the training, and this is going to make it more robust as well. Okay, we can trust our results better. Okay. Yes, correct. Okay, increasing K for K4 will make it more accurate and more expensive. Exactly. Okay, and it will take longer to run. Basically, expensive means more longer in terms of computational time. Okay, so increasing K4 will make your model more accurate. You can trust it better. Okay, so there's a sweet spot for K4. Okay, usually it's 10 folds, all right, or 5 folds. Okay, most of the time we will do 10. And then after that, but then depends on how long it takes for the algorithm to even train one model, right? Sometimes you just do 5 again. Okay, because there's also a bias variance trade-off thing going on with the K4. Okay, but we'll not go there. Okay, just there's also a bias variance trade-off thing over on the K4. Okay. So now let's look at this thing. Now leave one out cross validation. Basically, we have only one model over here. Okay, because we leave one out, we use everything, right? Okay, so we only have one mean square error. Now you see we can compare everything very nicely. We know that maybe we should use 7. Okay, 7 degree polynomial 7. Now what is on the right? 10-fold cross validation. Okay, what is 10-fold? Or each line here represents one instance of 10-fold cross validation. So each line I do 10-fold. Each line I do 10-fold cross validation. Okay, each line I do tenfold cross-validation. Now, why is there still some kind of like no difference, right? Because when I do tenfold cross-validation, I can still randomly select which are going to be my 10 folds, right? It doesn't have to be this 10. Like here, if I do 5 folds, it doesn't have to be this 5. I can make this, make this 5 a bit, this one a bit smaller, this one a bit larger, this one a bit smaller, this one a bit larger, right? I can have different 5s again, okay? So but if we do leave one out, there's no way, because surely there's only one that we leave out, correct? Okay, always will have this and this n data set, okay? But for here, for the k-fold, right, I can have a different 5 data sets here if I just split the 5 differently, right? I can make this orange bar shorter, this one longer, this one shorter, this one same size, then I have another different one. So that's why we have a little bit difference over here. But you see that this is much better compared to earlier here, right? Because what's happening, this is the power of the k-fold CVs, all right? Now you see that, the fluctuation between how we choose the training set and the test set, right, is not that much anymore. Then it's much better, right? Then we can trust our model that we don't have to worry about the data set being the problem. Then here we can see roughly where is good. If it were me, I might choose 2. Okay, I might choose 2 because there's not much improvement over the rest, correct? And remember again, we want the simplest model that can explain the best, right? So I think 2 is good enough. I will choose 2 actually, really, because this is the simplest model that I explain. You put 3, 4, 5, 6, maybe there's some chance of overfitting as well. Okay, you see there's not much improvement if you from 2 to 10, right? Basically the same. So I will just choose 2, the simplest model that can explain the data the best. Okay, give me the lowest mean square error. Does that make sense? There will be some trade-off, of course. Okay. So I think that's all, right? So these are the references. I highly recommend Introduction to Statistical Learning. It is a textbook, okay, that we teach undergraduate statistical learning from, and but of course you will need some math, like your math baseline must be a bit there. Okay, so it's not really that readable if you don't have the math background. Okay, if not, you can go to this Google machine learning crash course. Okay, I think that may be of use also, but this involves a little bit of programming. Okay, but the concepts are there as well. Okay, and this analytics video also, I think this is, if you search data analytics, this website always comes up on Google as well. Okay, so this one will be good, and this is another textbook. Okay, but the best textbook, if you really want to have a textbook, this Introduction to Statistical Learning textbook is the best. Okay, if you go at Google citations, right, this textbook has like 1,000 plus citations, 1,000 citations around there. Okay, this is the best textbook. I've looked at the textbook and I think it's really good as well. Okay, so I think I run over short, but it's okay. I hope as long as you guys have time, I'm also here. We can ask questions if you still have any questions. Really happy to take questions. So I hope I managed to, clear up, or maybe I don't make you all more confused, right? But at least introduce the terms of cross-validation. What is the idea of cross-validation, right? Okay. If you are confused, you can also ask me questions now, email, or when the recording is up, you can rewatch the recording, right? And hopefully that will help you understand. The slides will also be given to you guys, so that will be useful as well. Okay. Is there any questions? Or I hope usually when there's no questions, either people understand or they don't understand. I hope you understand. Okay. Because I was thinking if I want to put linear regression only, but then it's gonna be very difficult to teach a lot of linear regression in 1 hour. Okay. So I was racking my mind, what can I talk to you guys in 1 hour, and that is gonna be useful. Okay, and I hope this is useful, especially the cross-validation part and the bias versus variance trade-off. Okay, so the takeaway, if you have to take away, is bias variance trade-off. Okay, bias variance trade-off and cross-validation. Okay, these two things you'll always see in any machine learning. Okay, so Nicholas has a question on log regression, the difference between log regression and linear regression. So I hope you're not, okay, if my interpretation of the question is correct, you're not asking logistic regression and linear regression. You're asking when we take I anticipated the question, so I predicted this to have, right? Machine learning, right? Based on past data that I have, right? Of students, right? They always, logistic regression. Wait, so an understanding of your logistic regression, is it when you take logs of the variable y, or you're talking about, you know, not the logistic regression, the actual logistic regression. So the actual, okay, let's assume logistic regression, okay? The actual logistic regression is used for predicting categorical data, okay? Because linear regression is used for numerical continuous data, okay? But when you have category, your category is only 0, 1, right? You cannot use linear regression because linear regression predicts less than, from like minus infinity to plus infinity, not 0 and 1. So logistic regression is applying the logistic function, you can search logistic function, to the linear regression so that it will restrict the values that you predict to be between 0 and 1. Okay, you will restrict your regression to be between 0 and 1 so that you can predict, so then you will predict probabilities that is 0 and 1 depending on the cutoff that you choose. I hope that is a good explanation of Nicholas, because that's the best I can explain now like that about linear regression. Does that make sense? So logistic regression is for categorical data because categorical data is only 0, 1, 2, 3. That's it, right? We cannot go to 4 or 5 because categories, there's no category 4 or 5. There's no category -1. There's no category 0.1, 0.2, 0.3, right? It's just 0, 1, 2, 3. That's it. That's why you need to use logistic regression. Linear regression, when you do linear regression, once you have the equation, right, you can get 0.1, 0.2, 0.3, depending on the values they put in, right? You can get negative as well, you can get positive as well. Okay? So again, just to finish up the Nicholas question, okay, Raffiandra, wait a bit. So Nicholas, the approach testing is the same? Yes. So the good thing about what I teach you here now, cross-validation, okay? Cross-validation works for all machine learning models, okay? That's why I chose to do cross-validation, because no matter what is your model, right? Linear regression, logistic regression, random forest, neural networks, whatever, okay? You can always do cross-validation, right? This is the gold standard. Cross-validation is the gold standard, okay? Linear regression, there's R square, you know, there's adjusted R square, there's all those things, but those are all in-sample stuff, okay? You just, R square is based on your current sample, right? But in machine learning, in prediction, if we predict very well on in-sample, so what? You know, I'll just tell you very well in-sample, so what? What is the out-of-sample idea, right? The cross-validation will help you with the out-of-sample, and that is really what we are interested in, right? Like I said again, based on the slide, the cross-validation, in machine learning, our aim is not in-sample, our aim is to make very good predictions on new, unseen data, and cross-validation will help us answer this question. Okay, Raffiandra, you don't understand why there are so many lines in K4 CV than the LO. Okay, yes, let me repeat again. So let's think about it, okay? In leave one out cross-validation, I will leave one data point out, correct? But then in the end, I'll take turns. So these data points will take turns to leave out, right? They'll take turns. First, I'll leave the first one. Then I will leave the second one. Then I'll leave the third one. So finally, I'll leave the last one. Okay? There is no randomness here, right? In the end, how many bars do I have here? If my sample is n data points, I will have n bars here, right? Because there's no random, I will leave one at a time. There's nothing random. In each time, I leave out one only, right? So if I repeat this thing over and over again, every time I will just leave out that one thing and two things. That one, this first one, then after the next one, I leave out the second one and the third one, correct? So if I do the leave one out cross validation, there's only one line. There's no randomness in leave one out cross validation. Now in K4 cross validation, when K is not n, okay, because it's n, remember if it's n false just means it's leave one out, okay? In K4 cross validation, there is randomness involved. Why is there randomness here? Because how I choose this red color one, right? Oh, sorry, orange color one. I don't have to have the orange color one to be this bar, okay? Can I annotate? Okay, I don't have the orange color one to be this bar. Now here it is the orange color one, right? In 5 folds, this is 5 folds, I have this thing. Now I could make it so that my orange color part is this one, right? And then this orange color part is this part, right? And then the rest remains the same. Now this is going to give me a different training and test set compared to the earlier case, right? The earlier case, I only have this orange, these are the orange part. The second case is this orange part plus this purple part and this purple part only. And then this is going to give me a different mean square error. Does that make sense? Okay, so therefore we can do this many, many times. I don't have to take all these different parts. I can take this part again, and this part to be I can take this part and this part to be the first model, and then now I can use this part only to the second model, and this will give me again a different mean square error. Okay, so depending on how I choose, I'm going to get different mean square errors for the models. Does that make sense? Okay, Referendra? But for the leave one out, you see, I always will leave out this one and have this one, and then leave out this one, and then have that one. I always have this same step. No matter what I do, I always have this one because I'm only just leaving one out. But this one, I'm just saying, I just split the data into 5 portions. How I do that split of 5 can be random, right? It's not all the time the same, right? Because I can first split, this split, right? Okay, this split is what I've shown here. I can also, okay, so this is the 5 split, right? So let's ignore the bottom one. I can do this split, which is the split shown here. I can do another split that's like that 1. So this is 1 split, 2 split, 3 split, 4 split. Then this is another split, right? That is different from this split, right? So this split will correspond to 1 line on the next diagram. Okay, this split will correspond to 1 line here. And then there's the bottom split here will correspond to another line here. So there will be many, many different lines that you'll get. Okay, Rafendra? I hope you answered. Thank you. Chun Ng, you say, so the model with lowest, yes, the lowest with the lowest CV is best because in this case, we use mean square error as the error metric. Okay, for mean square error, the lower it is, the better. CV just gives me the average mean square error for these models. Okay, so CV is a method for getting average errors. You can change the mean square error metric to other things. There could be other metrics that maybe higher is better. Then CV will give you the average of all that metric, and then you take the highest one. Does that make sense? But in this case, because we are using mean square error, okay, then we will take the smallest mean square error. So the model with the lowest CV, not lowest CV, the lowest, so we will say the lowest cross-validated mean square error is the best. Okay? We can use root mean square error, which also lowest is best. Okay, but we will say the lowest cross-validated root mean square error. Okay? So you will notice that sometimes people will ask you, have you cross-validated your model? What they are trying to say is that, oh, did you do this process over here? Do you do the cross-validation? Right? Sometimes people will just do this one time. Then you will also get a mean square error, but it is not cross-validated because you never do this process. You never do this process of doing it over again on different parts of the data. You just do it one time. You will still get a mean square error, but it's not cross-validated. And then that's not a good model because you did not cross-validate your model. Maybe you just so happen to get this particular case over here, right? You miss out this one. Does that make sense? Okay. Nico, thanks for the link. So if you look at the question answer, Nico found a YouTube video to illustrate the difference between linear and logistic regression. So maybe you can have a look there as well, because I can't explain here without the slides and everything, right? So I can only give you the idea between linear and logistic regression. Okay. You can also look Wikipedia, right? Basically, it's a logistic function that we apply to linear regression, okay? So that we can estimate categories 0 and 1, okay? Is there any more questions? I don't want to keep you on here. You are free to go if you have anything on, right? Okay, but of course, I'm also still happy to take questions. So, yeah, for machine learning, it's about prediction, okay? So you have to be very careful what you're trying to do, okay? Because different models have different advantages and disadvantages. There are different assumptions, and you must make sure that those assumptions are satisfied before you can use them, okay? So just be careful about that, okay? So I hope it was helpful. The slides will be up, okay? Waiting for any questions, any more questions? So just a reminder, I guess for those who were late, this is my second last office hour with you guys. The following week, next week, there's no office hour. The following week there is, okay? And then after that is gonna be a faculty engagement session with the professors live in the same office hour in my same. So technically I still have an office hour, just that I converted that to a faculty engagement session for you guys, right? Because you guys are interested to talk to the professors, right? So I reached out to them and they are more than happy to do it. Okay, so they will come here and they will be live. They will be on Zoom and they can ask them questions, and exchange questions. Okay, so that will be the last office hour. So Nicholas, for the K4 testing, is the size of the orange box. Yeah, so it doesn't have to be the same. It just needs to be 5. Okay, it can be yeah, that's why it can be random, right? That's why we have all these lines, because the size of the box doesn't have to be like that. If it's as long as there are 5 different boxes, it doesn't even have to be together. Do you know what I mean? Okay, we can have boxes that are like that for this one is like that and like that, right? And then for this one is like that, and then for this one it could be just like that, and for this one it could be like that and like that, and for this one it could be this one. You know? Okay. Then this will give you another one. That's why we have these different lines over here. Okay. So the only thing that matters for K4 is that we split the data into 5 different training and testing data sets. Does that make sense? Okay. Jordan, yes, the session will be posted later. So in fact, all the sessions are always posted online after the thing. So you can find them in the module, right, on the office hours. Okay, Jordan, it will be posted online together with the slides as well. Okay. Can? So I hope I answered all the questions. Okay. Then thank you very much for coming. So we'll see. So next week I won't see you guys. Following week, then we'll see again, and then that's the last session for me, and then we have the professors after that. Okay. In the meantime, just feel free to ask questions on the Q&A board or email me the questions through the inbox. Right. Thank you. Thank you. Thanks, Janet. Thanks, Nicholas.